Welcome to a refresher on magnetic flux and changes of magnetic flux. I'm starting out with a board that just shows a magnetic field existing in some area of space. You can kind of see the field is stronger by the more field lines towards the right bottom hand side of the board. And the idea of magnetic flux is that if I were to introduce a ring, in this case I have let's say a copper ring, a conducting ring, into that magnetic field, we could talk about the amount of field that pierces or goes through the center of the loop. So the idea would be this: some of these field lines actually come in one side and kind of go through the center of the loop. That right there, that idea of the amount of field that goes through the loop is what we give the term magnetic flux to. And we give the symbol, the Greek symbol phi, which actually is kind of nice in terms of most of the symbols you have for physics are rather abstract. This one's pretty good. It looks like a ring with a field line through it. And you can imagine more field lines. In other words, if I increase the number of field lines here, I'd have more flux. Fewer field lines would be less flux. That's the idea of magnetic flux. Now for a magnetic flux here, we can imagine different ways to change the magnetic flux that goes through the loop. One obvious example would be I can change the amount of field going through the loop by just dragging the loop to an area that has a more intense field. And you can see if we were just, all we were doing is counting field lines, you can see a lot more field lines go through the loop. So we could say in this case that the magnetic field, therefore magnetic flux, increased. In other words, we could say that the magnetic flux is partly dependent on the strength of the field. You can imagine other ways that you might change the amount of flux that goes through the loop, the field that goes through the loop. And another way would be something like this: if we change the size of the loop. So pretty clearly, if I'm in this case expanding the loop, you can see there that we're capturing more field lines, and we will increase the flux. And in this case, I could drag it down someplace somewhat smaller, something like this, and grab only a small portion of the field, which means that our magnetic flux partly depends on the strength of the field, but then also depends on the area of the loop. The bigger the area of the loop, the more field lines that penetrate the inside of the loop. Now the last way that we could change the amount of field that goes through the loop is a little harder to show here. So what I'm going to do is I'm going to go ahead and draw in some other features so you have the perspective of this, right? You could imagine this ring that I have here having spokes, kind of like a bike wheel. You could imagine there are some spokes kind of going in this direction, in this direction, in this direction. And then the axis, or the let's say the axle of the bike, would be someplace here, and we could draw a line. In this case I'm going to draw let me try that again. There we go. I'm going to draw a line something like this that points in the direction that the axle points for my wheel, as it would be in this drawing. Okay, so with that little help there, you can kind of see that if I were to take my wire loop now and rotate the wire loop, something like this, you could see I could set it up to change the amount of field that goes through the loop. In this case, the loop is almost flat with respect to the magnetic field, and so the magnetic field lines don't actually even go through the loop at all. When I have it turned this way, you can kind of see that the maximum amount of magnetic field goes through. And if I were to change it in some direction like this, I would be changing it based on the angle. So it seems here that in this case right here, we could also introduce the idea of this angle right here, an angle between my axle, if you would, if that was a bike wheel, the axis of the loop and the magnetic field will partly determine the amount of field that goes through the loop, or my magnetic flux, that angle right there. Now when that angle is really small, as we showed, the magnetic flux is at a maximum, and when it is 90 degrees, we said it was 0, so that means that this must be a cosine representation here. So there, the cosine of that angle is going to play a factor in our magnetic flux. Now, why all of this discussion of magnetic flux? Well, it turns out that it's not the amount of field that goes through the loop that we're interested in. It turns out it's that if you change this magnetic flux, you get an electrical phenomena that happens in the ring, and that's what we're actually interested in. What we're actually interested in is this. We're interested in induced voltages inside of our conducting ring, and that induced voltage depends on the change in the magnetic flux in the loop over a certain period of time. Now, based on our representation that we've given before, that means that I could change the amount of field, the magnitude of the field B, that goes through the loop. I could change the area of the loop, or I could change the angle between that axle of the loop and the field. Any of those changes over a certain period of time will induce a voltage in my loop. Now that can be quite interesting, having a voltage in the loop, because that E, or EMF, electromotive force is the term for that, that voltage in a conducting loop will generate a current. And so we can also say that this setup of changing the magnetic flux that goes through a loop, we can think of it in terms of the induced voltage, or we can think of it in terms of this induced current that is in the loop. Now in the next tutorial, I'll refresh your memory on how we decide the direction of that current based on changes in magnetic flux. Thanks for joining me.